In our previous video, we showed uh, how to obtain the responses of AC circuits using time domain analysis. Uh, in that video, the process of obtaining the responses doesn't look uh, simple, considering that we use differential equations to derive the steady state responses. And that is only for series RL, RC, and RLC circuits. For networks containing series parallel combinations, that would um, result into a set of differential equations that would make the solution um, much more complicated. Now, in this video, we will present a new approach in solving for the steady state responses of AC circuits, and this would make the solution more straightforward and simple. The objectives for this video is to show you the transformation process from time domain to frequency domain in order to solve the steady state responses of AC circuits. Also, we will show you how to solve AC circuits using phasor analysis. To show the transformation process, again, let's solve for the steady state response of a series RL circuit. Here we have a circuit which is excited by a sinusoidal forcing function. And we already know that if we apply this function, uh, it will yield a steady state response that would look like this, where phi there is given by this formula for a series RL. Let's say I will add to my source another source, which is this one. So this source is a bit different because while this source is a real number, this one is an imaginary source due to the fact that we have an imaginary number, j, which is equals to square root of -1. The reason why I selected an imaginary source will become evident later in this discussion. So overall, what I'm trying to apply on the circuit is really a voltage that is a complex voltage because it consists of a real source and an imaginary source. So combining them together, that makes a complex source. So the question now is, what would be the response of the circuit? So given this complex source, let me write the response to be in this format. So what is this response all about? So by superposition principle, we know that the response is really a combination to the responses to the individual voltages applied on the circuit. So for example, if this is our voltage applied, that would give us this response. And if this is the voltage applied, that should give us this response according to superposition principle. And the combination of these voltages, this voltage here and here, should give us also the combined response for each of those voltages, which is this one. Simplifying, that will give us these equations. Recall that from Euler's identity, these expressions can be replaced by complex exponential expressions, and that should give us these much more compact equations. Now let's go to our circuit and write the KVL equation for that series RL circuit, which is this one. And let's substitute the values for I and E here from here and here. So that would give us this one. So notice that I have factored out these factors and that I should be able to cancel them out. So this is one, this is cancelled, this is cancelled. And that should give me this expression. Take note that our objective here is to solve for I sub m and the angle phi. Once we have these values, we can write immediately our steady state response. Now, uh, take note that 1 over r plus j omega L is also a complex expression, and that can also be replaced by an exponential, complex exponential expression, which is, I won't go over to the details, which is this one, where the angle beta is given by this one. I can write this in a more compact manner, like that one, and notice that in order for this equation to be true, I sub m must be equals to this one, and the angle phi must be equals to beta, like that one. So therefore, I can now write our steady state response. So we were able to obtain the solution for the steady state response by applying a complex source. Let me go back to this expression and discuss further what happened. This expression here is the frequency domain equivalent or form of this expression or the sinusoid in our circuit. This R here is the frequency domain equivalent of our resistance in our circuit. This one is the frequency domain equivalent of our inductor L in our circuit. And lastly, this expression here is the frequency domain equivalent of our steady state response, which we know to be equals to this based on our what we have done on our previous slides. So what we have done is transform our circuit, our time-dependent circuit, into another circuit which we call a frequency domain circuit or a phasor equivalent by transforming the components into its phasor equivalent, including the variables that comes along with the circuit. So the source here becomes this source here in the frequency domain equivalent or phasor equivalent. The resistance is still the same. L here became j omega L in the frequency equivalent. Now, take note also that we have transformed the variables. So the response now is this one, which we just write simply as capital letter I. So here is our circuit again in phasor form or phasor equivalent. The relationship of this and this one is given by this one, which we can simply write as that expression, which is just Ohm's law in the frequency domain, where this is our source and this is our um, the sum of the resistance and the inductive reactance in frequency domain, which is really the impedance of the circuit. So let's have an example to illustrate frequency domain analysis. So the first step is to convert the circuit into its phasor equivalent. So this is the phasor equivalent of the source. The resistance is still the same, and the inductance is j omega L. So we can solve the phasor I using Ohm's law in the frequency domain. So we need first to solve for the angle beta, which is this one. And now we can plug in the values, and we will get a phasor I, which is this one. And based on this result, we can get the time domain equivalent of the phasor I, which is actually this one. So I sub m here is really this number here. Omega is still the omega of the source, which is 125. Theta plus phi is negative 7.02 degrees. Phasors can be written in different forms. So we have the exponential, polar, and rectangular forms. In our last example, our source in time domain, which is a sinusoidal source, is converted into a phasor equivalent, which is this one, which is really the exponential form for obvious reasons. Our response in time domain form is this form in phasor, which is also in exponential form. So a polar form is just another way of writing an exponential form. So let's say we have this phasor in exponential form. So we simply write it this way, where we take this angle here and put it there. So this one is actually read as 300 angle bar 30 degrees. So this exponential form written as a polar form is this one. So we read this as 0.24 angle bar negative 7.02 degrees. The rectangular form is the equivalent of the exponential form as shown in the Euler's identity. So for example, we know that this one by Euler's identity is really this one. And if we simplify this, we will get this form. So this form is the rectangular equivalent of this exponential form. So our current is in a rectangular form is like this one. Now we can convert between polar and rectangular forms of the phasor. So for example, I'm given a phasor which is in polar form but that looks like this. I can get the phasor or the rectangular equivalent by using this. So, well, there is actually an A here. So given a phasor in rectangular form, A plus JB, we could get its polar equivalent by using this formula. So this one is really the use of Pythagorean formula and the angle can be determined by using inverse tangent. Now, in your scientific calculators, they are actually equipped with functions that assist in the conversion process. So I would recommend to see video tutorials on how to use those functions. So let's have another example. So let's say we have sinusoids here, and we are asked to convert them into polar or rectangular forms and rectangular forms. So this is how to do it. So for this sinusoid, well, you simply copy this, put it there, and the angle here is actually this one. So we can use the formula in the conversion to rectangular form from polar to rectangular, and we will get this rectangular form. Now for the second sinusoid, we we can write it immediately as this one in polar form. So bringing in the negative sign there. Um, we could also get rid of the negative sign by say adding 180 degrees to 75, and that should give us this one. So the polar form would be this one. So actually this one and this one are just the same, and that should give uh, a rectangular form that looks like this. Now for the third sinusoid, we're given a sinusoid in cosine. So we could write immediately in polar form that looks like this. So we simply copy again the magnitude here, the amplitude in here, and the angle in here. Okay, that would give us a rectangular that is like this one. Now, now let's say I don't want to use cosine, so I convert it to sine by adding 90 degrees to 50, so that should give me this one. So converting it to polar should give me like this one. Now these two polar forms are actually different. So how come they are different? Would that not give me a problem? So it's really just a matter of agreement that if we use this, it is understood that if I convert this back to a sinusoid, I should use a cosine function. And for this one, it is understood that if I convert this back to a sinusoid, I should use a sine function. So considering that both of these are different polar expressions, that should give you also different rectangular forms. Phasor diagram. So a phasor can also be pictured uh, by a diagram, considering that uh, um, the exponential expression has an equivalent rectangular expression, and it is really the sum of a real part and an imaginary part. So we could actually draw this like a vector in the complex plane. So for example, if I have this uh, phasor in polar and this is the rectangular, this would be its diagram in the complex plane. If I have this one, its diagram in the complex plane would be something like this one, which sometimes we draw it the length of the arrow as the same as the magnitude uh, of the phasor in polar form, and the real and the imaginary coordinates corresponds to the real and the imaginary terms in the rectangular expression. In order to solve AC circuits in frequency domain, we need to transform all the components into its phasor equivalent. So we already did that for resistance and inductance. So we said that the resistance is still the same between time domain and frequency domain. The inductance in uh, polar form is given by this one. So it's omega L angle 90 degrees. And in rectangular form, it is j omega L. For capacitor, it is this expression, and for rectangular form, this is the expression. So because we could express the components into its phasor equivalent, we could also draw them uh, their corresponding phasor diagram. For example, R would be like this one. The inductor would be directed upward. So this is omega L here, and this one is 1 over omega C, which is the for the capacitor. We could also manipulate phasors. So for example, we want to add two phasors, this phasor and this phasor. We will get a third phasor, which is really just like adding the two phasors in a vector-like fashion. So if we draw these two phasors, their phasor diagram, their addition would be like adding them as two vectors. Now for subtraction of phasors, that is also possible. So let's say we have phasor V1 minus phasor V2, we'll get a third phasor, which is like addition also, but with the phasor V2 reversed in its direction. And that can be done by adding or subtracting 180 degrees on the angle of the phasor. So what is the negative of the phasor? So let's say we have phasor A here. So let's say B is the negative of A. We simply take the opposite direction of A, and that should be the phasor B. We also can multiply phasors. So let's say we have phasor V1 and phasor V2. We get a third phasor where the magnitude is the product of the magnitudes of the two phasors, and the angle is the sum of their phase angle. Division is also possible. So we say we have phasor V1 and V2. What is V1 divided by V2? Well, we will get a phasor with a magnitude that is equals to the um, V1 divided by the magnitude V2, and the angle there would be uh, the angle V1, which is the angle in the numerator minus the angle of the phasor in the denominator. We could also get the square root of a phasor, and that would be the magnitude of that would be the square root of the magnitude of the phasor, and the angle would be half of the angle of the phasor. Now take note, we can only manipulate phasors that have the same frequency in their time domains. It is not valid to manipulate phasors that have different frequencies in their time domain. So that's it for this video, and our next video we will give more examples.